Okay, I have provided a separate video for a discussion for the purposes of just discussing inverse functions. Inverse functions, that should be a topic that you're already familiar with. That is something you do in a pre-cal class. So I wanted to separate that from the calculus side. And as far as the calculus part of inverse functions is concerned, this is going to be short. Okay, it's going to be very brief. First of all, there's a theorem that says the inverse function, the inverse of f, its derivative. Notice how these parentheses are written. The inverse function's derivative, if evaluated at some number a, is equal to 1 over the function's derivative evaluated at f inverse of a. The idea behind this is basically being able to evaluate a derivative for an inverse function when you have a function on your hands where it would not be easy to find the inverse and therefore evaluate directly. For example, if you had f of x equaling 2x plus cosine of x, if that's your original function, and you wanted to find f inverse, all right, if you're wondering what does f inverse of x equal to, if that's the big question, the procedure that you learn is to first rewrite this as a y. So first I'm going to call this y equal 2x plus cosine of x. And to find an inverse function, you exchange x and y. So I'm going to jump back over here to the inverse side. And this will give me x equal 2y plus cosine of y. All right. Again, the objective now would be solve for y. All right. And what you're going to discover is it's not easy. Not easy at all. All right. That would not be easy to do. So we have this theorem. Again, the theorem that says the inverse function derivative evaluated at a is equal to 1 over the function's derivative evaluated at the inverse of a. So let's go back to that function. All right. If f of x is the 2x plus cosine of x, the problem wants us to find the inverse function's derivative when evaluated at 1. All right. We should note that if you plug a 0 into this function, then you'll get 2 times 0 plus cosine of 0 is equal to 1. In other words, f of 0 equals 1. Right? So therefore, again, without having to actually solve for the inverse, if you want to find the inverse function's derivative evaluated at 1 without solving for the inverse itself, then what this theorem is saying is that you can evaluate the inverse's function at 1 simply by putting it into that formula, which is 1 over the function's derivative evaluated at the inverse of 1, which, all right, is going to be what? All right, which is going to be what? How are we going to do that? Well, we know f of 0 is equal to 1. All right, we know f of 0 is equal to 1. So that's just going to be 1 over f prime evaluated at 0. So I need f prime. Okay. Well, if f of x is a 2x plus cosine of x, then f prime of x, what's that going to be? Okay, what's f prime going to be? Well, the derivative of 2x would be a 2. Derivative of cosine would be a negative sine. Chain rule would say times 1. Right? So f prime evaluated at 0 is a 2 minus sine of 0, which is a 2. So therefore, it turns out that that is just a 1/2. Now, is that the only way to do it? Well, no. Okay, it's not. All right, it's not, but it's one way to do it. And I will point out, not to sort of, no, take away from what the book's trying to show you. Note that if you're going to use this, one important thing to note is that if you're going to use this, you have to know in advance what x was plugged into the original function to get that y. All right, and again, the y value I'm talking about is the y value for the original, which is the x value for the inverse. All right, but I have to know, or I have to be able to figure out that plugging a 0 in this function gives you the 1 if I'm going to find f inverse's derivative at 1. If they were to ask me, just to be honest with you, if they were to say f inverse its derivative evaluated at 17, for example, if that was the question, I'd have to figure out what extra plug in here to get a 17 there. And maybe that's possible, maybe it's not, maybe it's easy, maybe it's difficult. All right, but you still have to be able to figure out what x did I plug in to get that y value in the first place. So even though you do not have to outright find, you do not have to explicitly find the inverse function, you do have to be able to find the x value that, you find that x value that you originally plugged in to get that y. Now, another possibility, right? Another possibility would be, just to sort of offer another option. If your original function, I'm going to go back to some stuff I did before. If your original function was a 2x plus a cosine of x, and you exchange x and y, you can then implicitly find a derivative here. Derivative of x is 1. Derivative of 2y is 2y prime. Derivative of cosine y is a minus sine y prime by the chain rule. You can factor out a y and you can divide. And if you look at what I got here, compared to what we ended up with up there, this f prime of 0, okay, this f prime of 0 is the 2 minus the sine of 0. In other words, I still, even if I do it this way, I still have to be able to figure out that in the original function, a 0 is what you plug in to get this 1. I still have to be able to obtain that information. So no matter which way you do it, you still have to be able to figure out what x was it that I plugged in to get that y in the beginning.